anyway, we start the class first. So last week, we finished talking about geotextile reinforced wall. Okay, then right now we start talking about non-gravity wall. Regarding, we will have a cantilever wall, or we will have a struct support wall, and anchor support wall. And this is also the other type of anchor. But this type of anchor is not common in Taiwan. Okay, because in Taiwan, generally the slope scale is actually the loading is very large. So the slope scale using this kind of anchor is not enough. So reasonably, we will choose this type of anchor. Okay, then for this kind of reinforcement, the same. For our analysis, we still need to know the potential failure mechanism, and then by assuming reasonable failure mechanism, which means failure mode, and then derive the solution. So actually, for the failure mode, we have these 4 types. Okay, first one is cantilever wall. So cantilever wall, the deformation look like this. Okay, top part lift away soil. Okay, and of course this part is active side, and part of this soil will be passive side. When this wall, particularly this part, penetrate into the soil part, okay, this part, long enough. So you can see if we extend this part long enough, this side will become passive. Okay, this side become active. Can you imagine? Because it's flexible due to the deformation. When this part long enough, this side will be passive, this side will be active. I'm talking about the bottom soil. Okay, then this type of reinforcement, the wall become very deep. The bottom part actually do not influence the deformation too much. Okay, bottom part. That means stability will not increase with penetrating depth too much. Okay, so we have a efficient penetrating depth for this kind of slope. Okay, then the second figure is supporting wall with insufficient support length. Okay, that means penetrating depth is not enough. So it's possible failure mechanism perform like this. That means the overall structure move together, become a rotational failure. Okay, rotational failure. Okay, then the third one is also the supporting wall with insufficient embedded length. Okay, this part. Due to the above soil have anchor support, so this part of failure mechanism cannot reasonably propagate here. But still, the bottom soil have potential to move. So the failure is due to this part of stiffness is not enough. So they will perform like this. Okay, then the next one is the bending moment is too much. Okay, so the wall deformation perform like this. Okay, this kind of deformation performance happen a lot in excavation project, because for excavation project, bending moment is the main control factor. So the maximum horizontal deformation will appear around the excavated depth, roughly is here. Okay, that's in Taiwan case. I'm not sure about other countries, but in Taiwan, this kind of deformation happen a lot for excavation project. And then excavation project will be our chapter 6 topic. Okay, so we will discuss lots of this kind of value mechanism and analysis approach to understand how to analyze the excavation. Okay, anyway, we have those potential value mechanism. Okay, so the most simple one is cantilever wall. Cantilever wall, first one. So cantilever wall look like this. And then for its deformation, here, right hand side here is active zone. Okay, left hand side here is passive zone. Okay, then we have a turning point here. So below the turning point, this part becomes passive side. Okay, this part is active side. Remember, active or passive are determined by soil movement direction. Okay, so for this part of soil move that way, so it's active, and this part is compressed, loading, so it's passive. Okay. So we will find certain point which is a turning point. Okay, active and passive situation will be changed. Okay, then theoretically, the horizontal stress distribution will be look like this. Okay, active side, and then bottom is passive side. So here is the transition range. Okay, however, the transition range is very difficult to be capture actual distribution. Okay, this part very difficult to measure or capture its distribution. But we know due to the stress continuous condition, theoretically they have certain transition. Okay, so very difficult to determine this part of distribution, and last, previous researcher assume length change like this. Okay, this is an ideal situation. So we just suppose the transition is a gap, a jump. Okay, look like this. And then the turning point is here. Okay, clear? It's ideal assumption. Ideal assumption. We assume the stress distribution jump like this. Okay, and then this method we call as a fixed earth support method. Okay, then this part is the other way we analyze have the anchor support. So we call as a free earth support method. Okay, it perform like this. Wall deformation is left hand side, and earth pressure distribution is right hand side, and then anchor force depends on the installation direction. Okay, so we just suppose anchor force is this. And of course, it can have horizontal and vertical traction. Okay, and then we have a look. The symbol we use, HE here, is excavation height. Excavation height. So E is excavation. Okay, P is penetrated. Penetrated. So we use P. Okay, represent its outlook. Okay, then for cantilever wall, we use fixed earth support method. Okay, cantilever wall, fixed support method. Remember, for all point O is a turning point, so there is a gap. Become passive and active. Okay, there is a stress jump. Okay, and this right hand side is from active become passive. Okay, so P and A here is passive and active. Okay, U last mean upper. Okay, L mean lower. Clear? Okay, U mean upper, L mean lower. So we can work out lateral earth pressure coefficient. Okay, so we can work out KAH and KPH from previous concept. Okay, then we know here is active distribution. So we can work out its resultant here. Okay, resultant because of triangle. Then we know passive distribution and it's also triangle, so we can work out its resultant. Theoretically, these two will not be the same. Okay, they will not be the same. And last, we will have internal force here. Okay, because we from engineering statics, this force is internal force because we cut become two sections. Remember, from engineering statics, we have section method. So here we have an internal force. Okay. So we will have an internal force to balance. Anyway, they should achieve equilibrium. Okay. If they don't achieve equilibrium, that means this wall is moving. It's not reasonable. So they will achieve equilibrium. Okay? So we will have internal force here. And then for bottom part, we know active side. Okay, if we know the depth from point O, so we can work out this. So there is a resultant. And the same for passive side, we also can work out its resultant. Okay, of course, this part will also have an internal force here. Okay, then we check the procedure. So for upper part, we can work out. Here is turning point O. Okay, turning point O. This. Okay, so for upper part, we can work out lateral earth pressure, and then by considering its triangle, we work out the resultant. So which is active side resultant here. Okay, passive side resultant is here. Okay, then for its level arm, we consider from point O. So this distance is 1/3 of HO. And this distance is 1/3 of HE plus HO. Okay? So that's a level up. Okay, then for factor of safety consideration, we use 1.5. Okay, so we use 1.5. So 1.5, its component is resistance divided by driving. Okay, then for the passive, yes. Okay, movement is lower. So resistance provided by passive side, and driving provided by active side. Okay, so passive side is resistance. Resultant times by level up. And driving side is active resultant times by level up. I consider moment equilibrium, not moment equilibrium, right? Moment factor of safety. Okay, it's moment. Okay, and based on this situation, theoretically, we know this. Okay? And then we want to achieve this. So, we can use try and error to find out this. Clear? We know this for our design. Theoretically, we should know our excavative depth. Because excavative depth is determined by how much you should remove the soil. So we know this. We know the requirement. Okay? We know this. We know the requirement. 1.5 here. So by using try and error, we can work out H naught. Clear? So you should know that. It's very difficult. Theoretically, it's very difficult to use hand calculation. So generally, we will use Excel to do that. But it doesn't mean it cannot be performed by hand. Theoretically, you can roughly guess. When you have experience, you can roughly guess the potential range. Okay? So you know your trial roughly range is anyway, you find out this value. For experience and conservative consideration, we will directly times by 1.2. To make it become penetrating depth. Okay? Using factor of safety, try and error to work out HO, and then directly times by 1.2. Okay, that's mean increase 20%. And then to obtain penetrating depth. But it doesn't mean this one is enough. So we have to check it whether it's enough or not. Okay, then the checking procedure is shown here. From previous derivation, here we have R, internal force here. Okay, so R can be worked out by one minus the other one. So that's the difference, which is the theoretical internal force here for R. Okay, then for bottom part, lower, okay, L means lower. Bottom part, bottom part here. Okay, for bottom part, once we know HO, okay, and HP, okay, we know those information. Theoretically, we can work out passive resultant and then active resultant for lower part. So we can minor each other to check whether this difference is greater or equal to above resultant. Okay, if satisfy this situation, that means it's safe design. If not satisfied, that means our penetrating depth could not be sufficient, or stiffness is not sufficient. So we have to improve our design. Okay, so that's for cantilever wall analysis. Okay, then this part is for supported wall. We have a anchor type support. Okay, so passive side is here, and active side is here. Okay, then we have a certain depth, so 0.0. Okay, certain depth here. So actually, we can work out its bottom horizontal stress. And of course, we can also work out a passive resultant and active resultant. Okay, so active resultant based on triangular calculation. Okay, passive also the area is triangle. Okay, then active level up. Active level up. HE. Okay, so it's HE minus plus HP. So which is here. HE is here. Plus HP is here. Okay, but we have to minor. Sorry, not. We have a 2/3. 2/3. HE plus HP. HE plus HP. And we want to work out here. We consider from this point. Okay, yes, correct. Because we consider from this point S, okay? So our distance calculation, level up calculation is we have 2/3 HE plus HP. Okay, 2/3 is because the triangle is here. Okay, S is here. So resultant for this triangle, this active side triangle, still 2/3. If calculate from this point, is 2/3 here. Okay. So here is 2/3 HE plus HD here. But it's calculated from this point. Calculated from this point, top. Okay? But we want to know the distance is here. So we have to minus HS again. Okay, minus HS. Okay, because we want to know this distance. Originally, this part is this distance, so we have to minus HS. Okay, so that's how we derive this part. Okay, the same for HP. Okay, so we have also calculated from S. Okay, so we have this part of calculation. So this part is for bottom, 2/3 here. Okay, and this part is for above, HE minus HS. Okay, so we have passive side level up. Okay, again, we use factor of safety is 1.5 by considering moment equilibrium. Moment calculation for factor of safety. Okay, so passive side is resistant because it prevent rotational. So it's resistant. Okay, active side is driving. Okay, driving. So actually, factor of safety calculation can be expressed using this term. Okay, and then take a moment. We can solve the equation by obtain HP. Okay, by obtain HP. So we use this way. Okay, then next step is we take a moment on point O. Point O is bottom here. We take a moment from point O, and then we can solve the equation to obtain anchor force. Okay? And then we can check whether this situation our anchor support is enough or not. Okay? So we can obtain anchor force. Okay, then this part is once we obtain once we obtain T, so we can use this way also by considering factor of safety is 1.5. And then we can check the load. We can check the load for the support per unit length. Okay, what's the meaning of unit length? Because generally, when we install the anchor, it's impossible to become two-dimensional infinite distance. Okay, so we will generally will install probably every 2 meter or every 2.5 meter or every 3 meter. So they will have a certain space. Okay, so we will have a horizontal space here. So actually, each anchor, how much load it can provide times by space. Okay. So we can obtain the potential. I should say it's a equivalent situation for the anchor loading. So we follow this way to design anchor supported wall. And I still have time. Okay, then the other way is T also can be evaluated based on the horizontal force equilibrium. Okay, because we have a passive load here. Active loading is here. They are horizontal. Okay, then T have certain direction, and certain angle. So we use cosine alpha, make it become horizontal force equilibrium. Okay, we use this way. We also can work out the T requirement. Okay, and we have certain condition. Fs is only applied to the passive side to account for uncertainty on the soil parameter, and then associate passive earth pressure. So we cannot put Fs everywhere. We only can put Fs this side. Okay, here I want to emphasize one thing. You see, for bearing capacity, our Fs is factor of safety is Q ultimate divided by Q allowable. Okay? Sorry. It should be low case. Okay? That's bearing capacity. So you see, for geotechnical design, factor of safety can be determined by stress. Okay, here, I should say it's strength. Okay, it's stress unit. And then here, factor of safety can be determined by moment. Okay, moment. Okay, and also factors of safety can be determined by force for friction. Remember previous concept, we calculate the sliding value, so friction. So there is no common standard. How do we choose factor of safety for different problems? As long as your derivation is reasonable. So factor of safety can be determined. Each component can be decided by lots of different considerations. Okay, so we have this. So once we know for each safety loading from anchor, and then the anchor actual loading, theoretically they are determined by field test. So in the field, we will do the anchor test to know how much load it can provide. Okay? So based on this situation, we can decide its factor of safety. So for permanent design, we want the anchor factor of safety greater than 3. For temporary design, we want its factor of safety greater than 2. Okay. Okay, then anchor. We also need to consider its length. Its length. Okay, because we want to make sure, of course, anchor should have enough loading provided, but we also want to make sure the anchor length, which is reasonable long enough to be out of the potential failure mechanism. Okay, here is possible failure mechanism, so we have to make sure which is long enough. But too long is not a good thing, because anchor resistor, if too long, for our installation, they cannot perform that good compared to relative short anchor length. Okay, then for its potential length, we can determine, because it's based on this relationship, we can determine the potential anchor length should satisfy this situation. Okay, we just use the equation to work out the answer. Okay, remember, practically, maybe anchor will more than one layer. Okay, so for different depths, so its required length could be different. Okay, so we follow this example to do the cantilever wall design, or to practice the cantilever wall calculation. So we have a cross section here, and which is cantilever wall. So assume the groundwater level is very deep. Theoretically, if we use cantilever wall, we will have a reasonable good drainage. Because water pressure, cantilever wall, its stiffness is not very good. So water pressure go in, it can easily damage the cantilever wall. So we have to make sure cantilever wall water dissipation is reasonable good. Okay, then determine the embedded length of the wall by using fixed earth support method. So required factor of safety is 1.5. Okay, then follow ranking active and passive theory. We can work out KAH and KPH. Okay, then we know lateral earth pressure coefficient. And then lateral earth pressure calculation active upper part. So we follow this equation. Okay, we follow this equation. But O is turning point, turning depth. We don't know HO. Okay, excavated depth is 4 meter. So we don't know HO. So upper active side resultant can be expressed by this. Okay, upper passive side can be expressed by this. Okay, triangular calculation. And then factor of safety is 1.5. Okay, 1.5. And then we put this part come from here. Okay? Here is passive side. Here is active side. Clear? Just moment calculation. Okay, then they should be greater than 1.5. So by try and error, try and error, generally in sand. So it's a sand material. This value will be slightly bigger than excavation depth. Okay, that's the experience. This value will be slightly bigger than excavation depth. So by try and error, we work out 4.9 meter. Okay, and then I mentioned by experience design, we compulsory times by 1.2. So we work out the value is 5.88 meter for its penetrating depth. Okay, so resultant here, we already work out when we know H naught here, not H naught, H0, not HO, we already know HO, it's worked out from here. So we know HO, we know HE, so we can work out this part. Okay, and here is also HO. So we have this value, we also have active side value. So the internal force R is this. That's the difference from here. So we know this value. Okay, then we check the bottom side. Bottom side. Okay, then we check the bottom side. So we put the value into it. So we work out this difference, this difference, compared to internal force here. So that means the bottom provided resistance is greater than the internal force. So which is safe condition. So we can follow this design concept. Okay, but our design concept, we should use this penetrating depth, not this. We should use this. But for our calculation, you see, we always use 4.9. That's checking. That's checking. We use 4.9. But real design value, we use this. Clear? Okay. And when you design this value, keep in mind, don't ask the field labor to install a wall. Look like this. You can ask them to install a wall, this part, to be 5.9 meter or 6 meter. Because this distance is very difficult to make it. Okay, they will be angry. Okay? Clear? So it's make the labor more comfortable, which is also very important. Okay, here I want to mention that next Monday I will pass you can review your midterm exam paper next Monday. Okay, and why I choose next Monday? Because this week we have to, until tomorrow, okay, we have to make sure that's the next midterm exam content. So I need to make sure that our content is enough for next midterm. So next Monday will be review time. Okay? And any question for today's content? Any other question? Until tomorrow, we will know. Because that's the reason I want to use the limited time to deliver more. Otherwise, we cannot reasonably finish the overall content. Okay? Any other? Because I saw the next example is too long, we cannot finish today. So we finish class here, so see you tomorrow.